In this video, I will demonstrate the performance of factor analysis. Now, before we get into the actual demonstration of the techniques, I want to talk a little bit about the theory and some of the application behind when and why we would use factor analysis. Now, this technique is very different than many of the techniques we use in inferential statistics when we're basically trying to compare groups to look for differences, or even when we're doing correlations or regression, when we're trying to make predictions or find relationships among variables. Factor analysis is really more of a data reduction technique. It takes potentially a large set of variables and looks for a way that the data can be reduced or kind of summarized using a smaller set of variables or components. Now, it does this by looking for clumps or groups that have very strong intercorrelations within a set of variables. So this is very difficult to do by eye. We can look for correlations in a correlation matrix when we've got a small number of variables, but when we have a large number of variables, which can very often be the case in factor analysis, we might have 10, 15, 20, or even 30 or more variables that we're trying to kind of find intercorrelations and try and find a pattern to how these variables work together. So that's difficult to do by eye. So this technique helps us do that mathematically. So factor analysis techniques have a lot of different uses. It's used a lot by researchers, especially when we're trying to develop and evaluate tests or scales that measure a particular construct or a particular knowledge area. How this typically works is the person developing the scale starts with a large number of individual items or questions on a scale or a measurement tool. And then by using these analytic techniques in factor analysis, we can kind of refine and reduce these items into a smaller number of subscales that measure the construct together, but also maybe measure various aspects of that construct. So we can use factor analysis to reduce a large number of related variables to a more manageable number and also a more efficient number of variables to measure a construct. So we don't have redundancy in the measurement of a construct, but we're measuring all aspects of that construct. So there's kind of two main approaches to factor analysis that you'll typically see described. One is called exploratory and the other is called confirmatory. Now, exploratory factor analysis is used typically in early stages of research in which we're trying to develop a theory or to gather information about relationships among variables. But when we do confirmatory analysis, what we're doing is we're actually trying to confirm or test specific hypotheses or theories that we've developed concerning the structure or the construct underlying a set of variables. Now, confirmatory factor analysis is a lot more complex and very sophisticated, but it helps us confirm theories and helps us get a better understanding of what a scale or a test might actually be measuring. Now, the term factor analysis is kind of a generic umbrella term, and it can actually represent a couple of different but related techniques. Now, the two related techniques that fall under this umbrella of factor analysis, one is called principal components analysis, or PCA, and the other is just called standard factor analysis. Now, these techniques have a lot of similarities, but they can also, but they're also very different, and a lot of times people use these interchangeably when they talk about factor analysis in general. So they both are trying to do the same thing. They're trying to develop a small number of linear combinations within the original variables so that we can capture or account for as much of the variability in these correlations as we can. But they do differ in a number of different ways. In principal components analysis, the original variables that we're working with are transformed into a smaller set of variables that have very strong linear correlations or linear combinations. And so we're also looking at the variance in all the variables. In standard factor analysis, factors are estimated using a mathematical model. So the only variance that's analyzed is the shared variance instead of the total variance. Now, a way to summarize, some people might say, well, should I use principal components analysis or standard factor analysis? What's the situation I need to decide when I'm going to use each of these? Probably a good way to summarize this is if you're interested in developing a theory, you're kind of in a theoretical research situation, or you're looking for a theoretical solution that's uncontaminated by unique or error variance. In other words, kind of the perfect world situation where we don't have messy variance, we don't have error that's unaccounted for, then standard factor analysis is probably your choice. If you're interested in more of a practical application and you really want an empirical, kind of a real world summary of your data set, then principal components analysis is probably the better choice to do. So in this example, I'm going to demonstrate principal components analysis because especially in the fields of health sciences and medicine, it's probably in education as well. It's one of the more commonly used techniques because of what it's able to do for us. Now, a little bit of terminology we need to clarify with this. When we talk about factor analysis, a lot of people use that interchangeably to talk about standard factor analysis and principal components analysis, but they are very different. When we talk about principal components analysis, the outcome that we're getting is actually a set of components that go into this measurement tool or this measurement technique that we're interested in. They're not technically factors. We refer to them as components, so we have to be careful we use the proper terminology there when we're doing that. If you're reading a journal article and you see someone referring to the factor as an outcome within the umbrella of factor analysis, they're probably talking about standard factor analysis. When you see an author referring to components, then they did principal components analysis. Now, another area of confusion is the word factor itself, which has different meanings depending on the kind of statistical analysis that we're doing. When we do analysis of variance, for example, we refer to the factor as the independent variable. But in factor analysis, and more specifically principal component analysis, we don't use the word factor, we use component. But when we're doing standard factor analysis, factor refers to a group or clump of related variables. Not necessarily an independent variable per se, but a group or clump of related variables. So it's important to keep that clear when you're talking about this, and certainly when you're reporting the results of a factor analysis technique, that you be very careful with the terminology. Okay, so let's get into the application then. So there are three basic steps in the performance of principal components analysis. And the first step is assessing the suitability of the data for factor analysis. So much like many of the other techniques we talk about and use, we have these assumptions we have to meet. Well, it's not factor analysis or principal components analysis is really not that different. So there's two issues we need to consider in determining whether data is appropriate or suitable. Sample size, and then the strength of the relationship among the variables or the items within our measurement tool. Now, there's not a lot of agreement as to how big a sample should be, but unfortunately the recommendation is the bigger the better. So one way to think about this, however, is when we have small samples, the correlation coefficients among the variables are going to be less reliable because there's going to be more variability in them, so the R values that we get from these relationships tend to be less reliable. So factors or components obtained from small data sets do not generalize as well as those derived from larger samples, which makes sense intuitively. Many authors kind of talk about feeling comfortable with having at least 300 cases or at least 300 subjects or at least 300 measurement points when doing factor analysis or principal components analysis. You can obviously have a smaller sample size, and we could still have a very appropriate and valid factor analysis with smaller sample sizes, but we do have to take into account that there could be some unexplained variability, or the result we're seeing might not be as reliable as we're assuming it is. Now, other authors recommend a ratio of participants to the number of items you have in your measurement tool that you're trying to reduce or analyze. And so some authors recommend a 10-to-1 ratio, so 10 subjects for each item to be looked at in the analysis. Others suggest 5 cases for each item. So kind of somewhere within that range, I would say, would be the bare minimum. So if you've got 20 components in your or 20 items in your scale that you're looking to analyze, having a minimum of 100 subjects, between 100 and 200 subjects would probably be okay, but that would again be kind of a minimum. Okay, now the second issue, as I mentioned, is the strength of the intercorrelations among the items within your measurement scale or measurement tool. Kind of the standard is that these items need to have bivariate correlations of at least 0.30 or greater, an R value of 0.30 or greater. If there are only a few correlations above this level, then factor analysis might not be appropriate. And again, it's going to depend on how many items you have. But there are some statistical measures that we have generated by SPSS can help us determine the appropriateness of the interrelationships. And we'll talk in more detail about these later, but one of them is called Bartlett's test of sphericity, and then there's the Kaiser-Meyer-Olkin measure of sampling adequacy. So we're going to be taking a look at those as a way to determine suitability of data. And so Bartlett's test of sphericity uses a p-value, and so if we have a significant Bartlett's test, in other words, the p-value should be less than 0.05, then that passes that suitability test. And the Kaiser-Meyer-Olkin measure, it ranges from 0 to 1, and if we have 0.6, that's kind of the minimum value for a good factor analysis. So greater than 0.6 would be even better, with closer to 1 being obviously perfect. Okay, the next step then will be the actual factor extraction. And so again, or the component extraction in the case of our example here. So this involves determining the smallest number of items that can be used to best represent the interrelationships among those items. So there are a variety of approaches that are used to identify or extract this number of components. And some of the most common extraction techniques, again, are principal component analysis, which we're going to do. So in the example we're going to do, it's typically up to the researcher to determine the number of factors that you consider best in order to describe the underlying relationship. But we have to balance two conflicting needs. The first is to find a simple solution with as few factors as possible. So we want to be as efficient as we can in coming up with a tool that has the fewest number of factors or components. But we also want to make sure we're getting a complete picture and explaining as much of the variance in the original data as possible. So we have to strike a balance between being complete in measuring whatever it is we're trying to measure, but also being efficient in how we're measuring that. Now we have three measures that we can look at that help us determine how efficient and how in-depth we're being in our measurement of the variance and accounting for the variance. The first is called Kaisers Criterion. There's something called the SCREE test, and then something called parallel analysis. And we'll talk more in detail about that when we get into our example. But I'll just kind of give a summary of each of these. So Kaisers Criterion, we use something called an eigenvalue, and if we have eigenvalues of 1.0 or greater, then those are our items we want to keep. Okay, and so the eigenvalue represents the amount of the total variance explained by that factor. Now the SCREE test involves plotting each of these eigenvalues of each of these items and inspecting the plot scatter plot to find a point at which the shape of the curve starts to change direction and becomes horizontal. And again, we'll take a look at one of these later on. And then parallel analysis is used as kind of a quality control check, if you will. And so how this works is we compare the size of the eigenvalues that we've collected from our data, and we compare them to eigenvalues obtained from a randomly generated data set of the same size. So only the eigenvalues that exceed the randomly generated eigenvalues are retained. So it's kind of like comparing what we have in our data to kind of a null hypothesis. And if our data values exceed the null hypothesis, then we will retain them and keep them as part of the model. So this approach has been shown to be more accurate than the Scree test or Kaisers Criterion. Kaisers Criterion and the Scree test tend to overestimate the number of components. And so the parallel analysis technique is gaining popularity, especially in the fields of psychology and education. So especially if you're publishing in those fields or even in other fields, looking at all three of these criteria or techniques is appropriate, and certainly reporting the results of all those is also appropriate. Okay, so step 3 then, what's known as factor rotation and interpretation. So once our number of components or items has been determined, our next step is to try and interpret them. So to assist in this interpretation, the components are termed rotated. And what happens is this does not change the underlying outcome or solution. It presents a pattern of what we call loadings in a manner that's easier to interpret. So basically it's just showing you which variables clump together. Now there are two main approaches to rotation, resulting in either what's known as an uncorrelated or correlated factor solution. So uncorrelated rotation results in solutions that tend to be easier to interpret and report. However, they do require you to assume that the underlying constructs or items are independent, not correlated. So this approach allows for the factors to be correlated, but they are more difficult to interpret. Or I'm sorry, the correlated approach allows for the factors to be correlated, but they're more difficult to interpret as well as to describe and report. So in most situations in practice, the two approaches often result in very similar solutions, especially when the pattern of correlations among the items is very clear. So many researchers will conduct both techniques, both types of rotations, uncorrelated and correlated, and then report what's clearest and easiest to interpret. So I typically recommend starting with the correlated rotation, and that tends to work probably more precisely. So with these two broad categories of approaches, there are a number of different techniques provided by SPSS. And the most commonly used that we will see is called the Vert Max Method, which attempts to minimize the number of variables that have high loadings or high intercorrelations for each factor. So that's some of the theory and some of the basic application ideas behind principal components analysis. So let's go ahead and get into an example. So the example I have here, the data file, I have a series of 20 items that are attempting to measure the same construct. Okay, so this is a survey that you can fill out, and it's attempting to measure mood. So this is more of a psychological measurement, but certainly this could be a measure of someone's knowledge level. This could be a measure of someone's critical thinking. This could be a measure of physical performance of some kind. This could be a measure of some other construct like intelligence. There's any number of different things that you can measure that we typically would measure using these kinds of scales or survey situations. And so this is just an example of measuring mood, attempting to use different scales to measure the depth as well as the breadth of that particular construct. And so how this particular scale works, just to give you an overview, it's referred to as the positive and negative affect scale, or the PANAS scale. And how this works is there's 20 adjectives describing different mood states. 10 of them positive adjectives like proud, active, or determined, and 10 of them negative like guilty, nervous, afraid. So this is attempting to measure two underlying dimensions, positive affect and negative affect. So in order to explore the structure with our sample, we're going to do principal components analysis to try and figure out which items or combinations of items best measure this measure of mood, positive and negative affect. So our underlying research question would be then, what is the component or factor structure of this positive and negative affect scale? So previous research has suggested that a two-factor structure, positive and negative affect, works the best. But we want to discover, is the structure of the scale in our sample consistent with what has been found in previous research? So is our data going to match up with the theory? So we have 20 correlated continuous variables, and so each of these components, each of these items, 1 through 20, is measured using a scale from 1 to 5, with 1 being feeling very slightly or not at all about a descriptor. So if the descriptor is interested, you can either answer very slightly or not at all, and up to 5 is extremely. So this measures this in a continuous way, in an interval-based way, each of these 20 adjectives or scales. Okay, so the assumptions we have here are sample size. So again, ideally our overall sample size should be, having at least 5 cases for each of the variables. So that would be 20 times 5 would be 100. So we have 439 subjects. So we meet kind of that minimum idea of subject number. We meet the other suggestion of minimum of 300. So we seem to have an adequate sample size. Now the next we look at the factorability of the correlation matrix. So again, to be considered suitable for this analysis, the correlation matrix should show at least some of the correlations among the items having an R value of 0.3 or greater. Bartlett's test of sphericity should be statistically significant at p less than 0.05, and the Kaiser-Meyer-Olkin value should be 0.60 or greater, and we'll see that in the output. We want to also look for linearity. Again, we're talking about correlations here, so we're assuming these correlations are linear. Now, we'll do kind of a spot check of some of the scatter plots to make sure we don't have any curvilinear relationships. But typically, if we have an adequate sample size, as far as a ratio of cases to variables, that shouldn't be an issue. So if you meet that first assumption of sample size, meeting the assumption of linearity should not be an issue. Also, we want to look for outliers among the cases. Factor analysis, like many other techniques, can be sensitive to outliers. So as part of your initial data screening process, before we even get to doing factor analysis, we want to make sure our data is accurate, complete, and we also want to screen for outliers using perhaps the outlier labeling technique is a way to look for outliers and then deal with those in several different ways. We can trim them. If we've got a small number of subjects, we might decide to Winsorize those, or we could also use multiple imputation to replace values that might be missing. So there are several different ways we can make sure we have accurate and complete data, but we definitely want to do that. Okay, so our next step then is to do the actual analysis. So we're going to go to the Analyze menu. We're going to find Dimension Reduction, and then choose Factor. Okay, so the next thing we want to do is select all of our items. So all of our items in our scale, all 20 of our items, we want to select them all. Okay, and we're going to want to move them over into the variables box. All right, so I have all 20 items there. Okay, next thing we want to do is click on the Descriptives button. And in the Statistics section, make sure the initial solution is checked, which is the default. In the section marked Correlation Matrix, select the options Coefficients, KMO, and Bartlett's Test of Sphericity. All right, and then click Continue. And then click on the Extraction button. In the Methods section, make sure Principal Components is selected. So again, we're doing Principal Components analysis. There are other techniques which we don't have really the time to get into, but we're doing a Principal Components analysis, so we want to make sure that is checked. And then we can choose in the Analyze section, Correlation Matrix. In the Display section, select Scree Plot, and then make sure that Unrotated Factor Solution is also checked. In the Extract section, we want to select Based on Eigenvalue, or if we want to force a specific number of factors, which you may say I want to have a minimum of 5 factors or components to my item, then you can force that number, and you can then type in that number. But we're going to base it on the eigenvalue. Then we click Continue. Then we click on the Rotation button. Choose Direct Oblimum. And press Continue. Click on the Options button. Now in the Missing Values section, click on Exclude Cases Pairwise. So again, if we do have some missing data, if a case or a subject has missing data, we'll exclude them. In the Coefficient Display Format section, the one just below that, click on Sorted by Size and Suppress Small Coefficients. Okay, and remember we talked about the value of 0.30 being the value that is kind of our threshold, our minimum. So we type in that value, so 0.30. So any coefficients that are below 0.30, we won't use those. So only the loadings or only the intercorrelations among variables above 3.0 will be displayed, so it'll make it a lot easier for our output to interpret. Then click Continue, then click OK. As you can see, we have a lot of output generated, and so it gets a little confusing to go through this, but we will follow this in a step-by-step procedure. So first we want to interpret the output. Okay, and our first step is to verify the data set is suitable for factor analysis. So we're going to check that the Kaiser Meyer-Olkin measure of sampling adequacy, or the KMO, which you're going to see in this table right here. We want to make sure that value is 0.60 or above. And as you can see here, our KMO value is 0.874, so that's good. We also want to look for Bartlett's test to be significant, so we're going to look at the SIG value of Bartlett's test. We want that value to be less than 0.05, and in this case it is. Therefore, factor analysis is appropriate for our data. Now, in the correlation matrix just above it, we can look for correlation coefficients of 0.30 and above. If you don't find many, we might want to reconsider. But as we start to look through this, we can see several. I'm looking at column PN2 here. We can already find several that are 0.30 or greater. There's 0.462, there's 0.645, 0.41, 0.5, and if we just kind of eyeball through the rest of these correlations, we can see that we've got numerous correlations above 0.30. So we're meeting that second assumption. Second step in our interpretation, we need to determine how many components to extract. So we need to consider a few pieces of information in the output. So using Kaisers Criterion, we're interested only in components that have an eigenvalue of 1 or more. So to determine how many components meet this criteria, we need to look at the total variance explained table, which we go to our table of contents here is this table. So we need to scan down the values provided in the first set of columns. So this first set labeled total, we want to scan that. Initial eigenvalues, okay? The eigenvalues for each component are listed. So in this example, only the first 4 components have eigenvalues above 1. So we can see component 4, 3, 2, and 1 are the only ones that have eigenvalues above 1.0. So we can also look at the percentage of variance that each one explains. Okay, so component 1 explains about 31% of the variance, 2 explains 16%, 6, and then 5%. And we can also look here at factor 4. This gives us an idea of the cumulative percentage of variance explained by these 4 components, and that is 60.13%. So these 4 components explain the majority of the variance within this set of data. So that's good. We'd like to have at least the majority of the variance explained by our factors or our components. Now, step 3, using the Kaiser criterion of that eigenvalue of 1.0, we might find that too many components have been extracted. In other words, we can't just count on the Kaiser criterion by itself. So we also want to look at the scree plot. So if we click on scree plot, we can see that in this table. So what we look for is a change or an elbow in the line graph. Okay, so only components above this break or elbow are retained. So in this example, it's quite clear that we have a break right here, or an elbow right here, between the second and third components. So components 1 and 2 explain or capture much more of the variance than the remaining components. So from this plot, I would recommend and suggest retaining and extracting only 2 components, because right here between 2 and 3 we see this break. So it appears that these first 2 components explain a lot more variance than the remaining components. Now there's another small break between component 3 and 4. We see this other little dip right here after the 4th, and there's another one right after this 4th component here. So depending on the research content, we might also want to consider retaining those factors because of that dip. So remember, this is a data exploration technique, so there's not always kind of this black and white demarcation point or decision point. So the interpretation, we very often have to kind of use our best judgment. We don't always have hard and fast rules we can stick by. So we might try several different combinations of components to see which seems to work the best. Okay, the third way, the next step, and the third way we can determine our extraction is that parallel analysis that we talked about. Now, in this procedure, we're going to need the list of eigenvalues provided in the total variance explained table. So in order to do the parallel analysis, SPSS doesn't have a function that allows us to do the parallel analysis. So we're going to use a program that's been developed outside of SPSS. And what I'll do is in the description for this video, I'll post the link you can get to and download this small application that you can use to help do the parallel analysis. So the program we're going to use is something called the Monte Carlo PCA for parallel analysis. And so the program asks you for 3 variables. So in our case, or 3 pieces of information. So in our case, it's going to ask for the number of variables, which is 20. We've got 20 items in our scale here. The number of participants in the sample, in this case we've got 435. And it's going to ask for the number of replications that we want. So what this is actually going to do, it's going to generate that random set of eigenvalues that we're going to use to then compare to the eigenvalues from our data. So we're going to specify 100 replications. Okay, and then we click on Calculate. And what it's actually doing is generating 100 sets of random data of the same size as our data, 20 variables times 435 cases, and it will calculate these kind of average eigenvalues for these 100 randomly generated samples. And so you'll see here in the table, here are these randomly generated eigenvalues. And so our job then is to systematically compare the eigenvalues that we obtained in our data in SPSS with the corresponding first value produced by this program, this Monte Carlo PCA program. So if our value from our component, in this case component number 1 has an eigenvalue of 6.250, if it is larger than the criterion value from the parallel analysis, which in this case is 1.39, then we can retain that factor, that component. If it's less than, we would reject it. So as we look through these eigenvalues from our data, and then for each component, and then compare them to this random eigenvalue from the parallel analysis, we can see that there's only two factors that we should retain. Factor number 1 and factor number 2. They both have eigenvalues that are greater than the eigenvalue from the parallel analysis. So factors 3, 4, and 5, or components 3, 4, and 5, for example, do not exceed the random value generated by our parallel analysis. So we're only going to retain 2 components for our analysis. So as you can see, we used 3 different steps or 3 different ways to determine which components we want to retain, and these 3 comparisons seem to agree with one another fairly well. So we can feel pretty confident that the 2 components are probably going to be our best option. Now you could argue that components 3 and 4 were very close, so you could argue that especially component 3 we might want to keep, but based upon this result, I would say probably the conservative approach would be just to keep the first 2 components. Okay, so moving back to our SPSS output then, our next step is, and the final table we need to look at, is the component matrix, which is this table here. Okay, this shows the unrotated loadings of each of the items on the 4 components. So SPSS uses the Kaiser criterion. It retains all the components with eigenvalues above 1 as the default. And then as you will look at this table, you'll see that most of the items load quite strongly. They have values 0.40 or greater on the first 2 components. So we can see these values here are all above 0.4. If we look at the second component, we can see the same thing. We can see values above 0.40 for the most part. So very few items load or interrelate on the third component, and there's only a pair of them on the fourth component. So what this is telling us is that the first 2 components have the best and the strongest interrelationships among these different items. And so we want to stick with the components that have the greatest number of interrelationships and the strongest interrelationships. So this again kind of confirms that our 2-factor component is probably the most appropriate. All right, the next step and the last step before we make a final decision concerning the number of components is we should take a look at the rotated 4-factor solution that is shown in the pattern matrix table. So this shows the item loadings on the 4 factors with 10 items loading above 0.3 on component 1. So these 10 items load above 0.3. 5 items load above 0.3 on component 2. 4 items on component 3, and only 2 items on component 4. So ideally, we'd like to have components that have 3 or more items loading, so the solution is not optimal for component 3 or component 4. So this again further confirms that a 2-component solution is our best option, is the most appropriate. So we obtained a 4-factor solution, but we've decided that we only want to keep 2 factors. So we only want to have a 2-factor or 2-component solution. So we need to force SPSS into using the data that creates a 2-component solution. So in order to do that, we're going to go back to the Analyze menu, Dimension Reduction, Factor, and we want to go back to the Extraction button. That's the only thing we're going to need to change. And we're going to click on Fixed Number of Factors. And in the box next to that, we want to include the number of factors we want to extract or components we want to extract. In this case, 2. We've decided we want to go with a 2-component or 2-factor model. We then click on Continue and then click on OK. So now we're kind of to the second stage of the interpretation of our output, where we're looking at the rotation of our 2-factor solution. And again, this is going to help us determine the suitability of this 2-factor solution or 2-component solution. So the first thing we need to check is the percentage of variance explained by this 2-factor solution, and that's shown in the total variance explained table. So for the 2-factor solution, we're only explaining about 48% of the variance, okay, compared by over 60% of the variance explained by that 4-factor or 4-component solution. So after rotating this 2-factor solution, there are 3 new tables at the end of the output we need to look at. And the first one is we need to have a look at the component correlation matrix. And this is going to show us the strength of the relationship between the 2 factors. In this case, it's fairly low, or quite low, at 0.277. So this gives us information to decide whether it was reasonable to assume that the 2 components were not related, or whether it is necessary to use and report the rotation solution that we used here. So in this case, the correlations between the 2 components are quite low, so we would expect very similar solutions from either of the types of rotations, either the Vert Max or the Oblimin rotation. So if the components are more strongly correlated, however, we have a value above 0.3, we may find discrepancies between the results of the 2 rotation approaches. So if that's the case, you need to report the Oblimin rotation. So Oblimin rotations provides 2 tables of loadings or interrelationships. The pattern matrix in this table shows the factor loadings of each of the variables, each of the items, excuse me. So we want to look for the highest loading items on each component to identify and label the component. So in this example, the main loadings on component 1 are items 17, 12, 18, and 13. 17, 12, 18, and 13. So those are the highest loadings. So if we refer back to the actual items themselves, as we talked about, you will see that these are all positive affect items. Okay, enthusiastic, inspired, alert, attentive. So the main items on component 2 are the negative affect items, 19, 14, 3, and 8. And these are all negative affect items. So in this case, it's really important to kind of know what each of your items are measuring and telling you, so that we can kind of make this interpretation. So in this case, identification and labeling of the two components is pretty easy, but this isn't always the case, unfortunately. So it looks like the two components are giving us that separation that we're looking for, that one component is all positive affect items and the second component is all negative affect items. So we're getting the separation that we expect to see. So now the structure matrix table, which is unique to this oblimon output, provides information about the correlation between variables and the components. So if we need to present the oblimon rotated solution in your output or in your results section, you have to present both of these tables, the pattern matrix table as well as the structure matrix table. Okay, now another table we want to look at that's up a little farther in our output, the Communalities table. This gives us information about how much of the variance in each item is explained. So how well does each item in the tool explain variance. So low values, less than 0.3, could indicate that the item does not fit well with the other items in its component. So for example, item number 5 has the lowest value, 0.258, for this solution, the two-factor solution. If we look at item 5, 0.258, it's got the lowest value. And it also shows the lowest loading on component 2 back in our pattern matrix table. So item 5 in component 2 has the lowest loading, the lowest interrelationship. So if we're interested in improving or refining the scale, making it more efficient, you could use this information to start to remove items from the scale or the measurement tool. So removing items with low communality values tends to increase the total variance explained. So the communality values can change dramatically depending on how many components are retained. So it's often better to interpret these values after you have chosen how many factors you want to retain using the scree plot and the parallel analysis. So you could argue that removing item number 5 might improve the efficiency of the analysis, and you can go ahead and do that, remove it, and then rerun the analysis to see if that explains the percentage of variance explained. Now, that's pretty much the analysis, but I have to warn you that this example was pretty clean, a pretty easy example. There wasn't a whole lot of messiness involved in it. Each of the variables loaded very strongly on one component or the other. So we saw that separation, that dichotomous separation between certain items loading on component 2 and certain items only loading on component 1. Sometimes we get items loading on both. And so when that happens, that indicates that there might be some overlap there or some confusion as to what an item is actually measuring. And again, each component is represented by a number of very strongly loading variables. We saw very high values, 0.80, 0.825, excuse me, 0.781, and so on. So with your data, unfortunately, you probably won't always have this nice straightforward result. So often we'll find that variables will load moderately on a number of different components, and some components will only have 1 or 2 variables that load for them. So in cases such as this, we might need to consider rotating a different number of components, maybe one more or one less, to see whether an more optimal solution can be found. So you might have to do several rotation analyses in order to pick out which components are really providing the best level of loading. So if we find that some variables just do not load on the components obtained at all, you may also need to consider removing those items and then repeating the analysis. So again, this was really just an overview of this technique. There's a lot more reading that you could do on this technique, a lot more in depth, and I would strongly recommend doing some additional reading, and I'll provide some resources for additional reading on factor analysis for you to take a look at. These tend to be pretty easy to follow books. And so I think these will be useful for you as you do the factor analysis. So factor analysis, or in this case specifically principal component analysis, we talked about taking a survey or measurement item that's attempting to measure a particular construct and try to find the items within that measurement tool that most efficiently and most precisely measure the construct that we're interested in. So hopefully you learned something from this video, and hopefully you have good luck using this technique in your own research.